In 6.2, we're learning about the fundamental theorem of calculus. Before we dig into the notes on page 84, let's go to a simple example because we've already learned about the fundamental theorem of calculus a little bit. So imagine this conveniently easy scenario. Let's say that you were traveling in a car at a constant velocity of 50 miles per hour and you're headed in the direction due west of, let's just say, of your home. So v of t, which is graphed below, models your velocity. So when you began this journey at t equals 0, so time t equals 0 hours, let's say you were already 200 miles away from your home due west. So if we are asked how many miles do you travel between t equals 0 and t equals 3? And I chose a simple problem because you could answer that without calculus. But what this is really asking is, let's say that x represents our position. So if we want to find our change in position, we would need to integrate our velocity between 0 and 3. So that's really what that first question is asking us to do. And don't forget that position, if I use x for position, the derivative of position is velocity, and we know the derivative of velocity is acceleration. So we said simply we could do this using the area under the curve. So from where x equals 0, or t equals 0 rather, to t equals 3, we would just find that shaded area. So 50 times 3, since it is a rectangle, is 75. So that tells us that you travel 75 miles between 0 and 3 hours. So the second question, and this is what really gets at the fundamental theorem of calculus. How many miles are you away from home at t equals 3? Well, remember, we were told that when you began this journey, you were already 200 miles away from home. So if we're using x to represent position, we know x of 0 equals 200 miles. And we might call that an initial condition. Then we also know that the definite integral of v from 0 to 3, that gives us the change in x, so the change in position between t equals 0 and t equals 3. So what we learned in Unit 5 is that to answer this question, if I want to know x of 3, that's going to be x of 0 plus the change in x from 0 to 3. And we get that by integrating the derivative of x, which is velocity. All right, so I'm not so much concerned with the answer here. Hopefully it's 275. But what this really does is this actually is going to demonstrate for us the first fundamental theorem of calculus. And so what I'm going to do is I'm going to take this equation and I'm going to subtract x of 0 from both sides of the equal sign. And that's going to generate this new equation that x of 3 minus x of 0 is equal to the definite integral of v of t dt. And it's important to keep in mind that v is the derivative of x, or x is the antiderivative of v. So, in short, what we see is that this definite integral, we can take the antiderivative of v. So I'm going to write down here, x is the antiderivative of v. And once we find the antiderivative, we can evaluate it at the boundaries or the limits of integration and then subtract. And we subtract the top limit from the bottom. So the antiderivative evaluated at the top limit of integration minus the antiderivative evaluated at the bottom limit. And like what we have there is the first fundamental theorem of calculus. We've already been using it to find what we might call a future value. So like when we find x of 3 equals 275, it's really the first fundamental theorem that we've been using. We just haven't called it that yet. All right, so let's go over to our notes, on page 84. And we can see illustrated nicely in the box the first fundamental theorem of calculus, where capital F is the antiderivative of lowercase f. And the important thing to remember here is that when we subtract, we always do it from the upper limit of integration to the lower. So whatever is on top here goes here, whatever is on bottom gets subtracted. So in section 6.1, we learned that when we find an antiderivative, that we have to include a constant of integration. And I'm going to show you one time in this first example why we do not need to find the constant of integration here. So for this first example, instead of evaluating the definite integral, I'm going to find the antiderivative with the indefinite integral first. So if I just drop the limits from 2 to 5, I'm going to use the rules from 6.1. So I know I've got to add 1 to my exponent. And then to account for the coefficient, I've got to either divide by 3 or multiply by 1/3. And then we would say plus c, where c represents some constant of integration. So now, since we know that that is the antiderivative of x squared, if we wanted to evaluate that from 5 to 2, here's how we could write that. We could write 1/3 x cubed plus c, then we could draw this long bar, and we could show the lower limit and the upper limit, and then an equal sign. And then when we plug them in, we always start with the upper limit. So we would have 1/3 times 5 cubed plus c minus, and then because we're going to subtract two terms, I'm going to use parentheses, 1/3 2 cubed times 2 cubed plus c. All right, so 5 cubed is, let's see, 5 cubed is what, 125? So we get 125 thirds plus our constant of integration. And then as I subtract, I'm going to drop the parentheses. So that would be minus 2 cubed is 8, so 8 thirds. And then remember that that subtraction applies to both terms, so minus c. So what happens is our constant of integration gets subtracted back out. So because of that, when we evaluate a definite integral, it is not necessary to add the constant of integration. All right, so we should get 1/17/3 for that first answer. All right, I'm not going to include the constant of integration on the rest of these because it's just more writing and it's unnecessary. So in our next example, we're going to evaluate the definite integral from 0 to pi/4 of 3x minus the sine of x dx. And the parentheses there are just so that the dx applies to everything in parentheses. All right, so here's how I would write this. Because we're going to go straight to the antiderivative, you can go ahead and put an equal sign here. Then when we take the antiderivative, like we are no longer going to write the symbol for integration because we are like executing that operation in this line. So the antiderivative of 3x, would be 3 halves x squared, and then negative sine of x would be positive cosine of x, because remember the derivative of cosine would cause that to become negative sine. And then I can't leave it like this. I have to show that I'm going to evaluate this antiderivative from 0 to pi over 4. So I'm going to draw a straight line at the bottom, my lower limit, at the top, my upper. And now on the other side of this line, I can plug these in. So I have 3 halves times pi over 4 squared plus the cosine of pi over 4 minus, and then I must put this in parentheses since I'm subtracting 2 terms, 3 halves times 0 squared plus the cosine of 0. All right, so that becomes, let's see, 3 halves times pi over 4 squared is 3 pi squared over 16 times 2, 32. The cosine of pi over 4, I know, is root 2 over 2. Minus, let's see, this all becomes 0, and then the cosine of 0 is 1. So we could get like denominators, or we could just leave it. All right, the third example. All right, the antiderivative of 4e to the x is just 4e to the x, and we're evaluating that from ln of 2 to 3. So that first fundamental theorem tells me to plug in the upper limit first. So 4e cubed minus the antiderivative of the lower limit, so 4e to the ln of 2. Out to the side, remember that e and natural log are inverses. They undo each other. So we're just left with the 2. All right, so that is 4e cubed minus 4 times, and that was e the ln of 2, so 4 times 2. So we're left with 4e cubed minus 8. All right, the next two that are on page 85 are a little more difficult because remember that there's no product rule and no quotient rule for integration. Okay, so we need to rewrite these before we can integrate. So if we just take the expression, the square root of x times x plus 1, well, I could think of that as being x to the 1/2 power times x plus 1. And we can distribute x to the 1/2 power over the binomial x plus 1. So what we're left with is the definite integral from 1 to 9 of x to the 3/2 power plus x to the 1/2 power dx. From here, we could use the properties of integration that we learned in 6.1. So our definite integral, actually, I don't really know why I'm rewriting that, sorry. Okay, so we'll go ahead and find the antiderivative. So that's going to be x to the 5/2 power, because we have to add 1, and 2 over 2 is the same as 1. And then 2/5 needs to be our coefficient, the reciprocal of 5/2, so that when we multiply by 5/2 taking the derivative, we have a coefficient of 1. And then plus x to the 3/2 power, but same thing, 2/3 needs to be our coefficient. And then we're going to evaluate this from 1 to 9. So we have 2/5 times 9 to the power of 5/2 plus 2/3 times 9 to the power of 3/2 minus, oh, I'm writing too big, in parentheses 2/5 times 1 to the power of 5/2 plus 2/3 times 1 to the power of 3/2. Okay, so 9 to the 5/2 power is 3 to the 5th, right? Because we could take the square root. So 2/5 times 3 to the 5th plus 2/3 times 3 cubed minus 2/5 times 1 to the 5/2 power is just 2/5. And then I'm going to distribute that subtraction and drop the parentheses, so minus 2/3, since 1 to the 3/2 power is just 1. Okay, so that becomes 486 over 5, 3 to the 5th times 2. Right here we could say that this is really 2 times 3 squared, so plus 18 minus 2/5 minus 2/3. We should get 1,712 over 15 when we combine our like denominators and get like denominators for our final answer. All right, the last example, again, we said there's no quotient rule, so we have to rewrite the expression in our integrand. So I could rewrite this first as x squared over x plus 3 over x. And then we could simplify that. Well, x squared divided by x is x. And then I'm just going to leave this as 3 over x. All right, and now we can find the antiderivative. So the antiderivative of x is 1/2 x squared. The antiderivative of 3 over x is 3 times the natural log of the absolute value of x. And we're going to evaluate that from 1 to e. All right, so when we plug in e, we have 1/2 e squared plus 3 times the natural log. You can drop the absolute value sign when we plug e in because e is already a positive number. And then we're going to subtract from that 1/2 times 1 squared plus 3 times the natural log of 1. Same thing, drop the absolute value because 1 is positive. All right, so we have 1/2 e squared. The natural log of e is just 1, so this is like 3 times 1. So that's just plus 3. And then minus 1/2. And then minus 3 times the natural log of 1. But the natural log of 1 is 0. So it's like minus 0. All right, so we end up with 1/2 e squared plus 5/2. Or if we wanted to, we could write that as e squared plus 5 over 2. For the last example, we're going to need to put this function in our graphing calculator. All right, so we are told that oil is being extracted from a well at a rate of E of t, and we're given the function E of t, and then we're asked first to determine at what rate is the oil being extracted at time t equals 2. So I know we could do this without a calculator, but let's do it with. So this is asking us for E of 2, since E is the rate at which the oil is being extracted. So the first thing we want to do is go into y1 and plot, or not plot, but write in our expression for E of t. So 3x cubed, since we can't make that a t, minus 2x squared plus 1. And then if we quit out of that, so second mode, if we want to evaluate E of 2, since we stored e of t into y1, in the calculator, we're going to evaluate y of 2. So we're going to go to vars, y-vars, function y1, because that's where we plugged in e of 2, or e of t rather. And the calculator knows function notation, so you have to use parentheses, and we get 17. And so if we include our units, that would be 17 gallons per hour. Don't ever use calculator notation. So even though we plug that into y1, like don't say y1 of 2. The function's not named y, the function is named e. All right, so the next question, we are asked what is the total amount of oil extracted from the well on the interval from 0 to 10. So if E represents the rate of change, so the rate at which the extraction of oil is changing essentially, or rather the rate at which oil is being extracted, that makes more sense, then the total amount extracted we must integrate. So what this is asking is from 0 to 10 for us to evaluate the integral of E of t. And we can do this in a calculator. So if I go to my calculator, if you go to math, and then if you see option 9, FN int, that stands for finite interval, or integral, excuse me. So you could either touch the 9 or you could just scroll down there and hit enter. And if you have the new operating system, it's going to show you this. So I want to plug in a 0 for my lower limit, a 10 for my upper limit. And then I need to plug in where I stored my function, which was in y1. So vars, y-vars, function y1. And then you always have to plug in the limit, the variable of integration, which is x. It's always going to be x. All right, we hit enter, and we get 68.43 1/3. Even though it's a third, let's take that out to 3 decimal places. Do not use the repeating bar. And that would be measured in gallons. Lastly, is the rate at which oil is being extracted increasing or decreasing at time t equals 4? So this is asking if E, because the rate at which oil is being extracted is E. So we want to know if E is increasing or decreasing. So in order to know that, we need to know if the derivative, E prime, is positive or negative. We can also use the calculator to evaluate the derivative at a particular value. So since we need to know specifically if E prime of 4 is positive or negative, in our calculator, if we go to math, and if you see option 8 where it says in deriv, select that. And the first thing is we have to type in our variable of the derivative, so that's d dx. And then we stored our derivative in y1. So vars, y-vars, function y1. And then lastly, we're evaluating the derivative at the particular value of t equals 4, or on the calculator x equals 4. So we hit enter, and it gives us E prime of 4. So E prime of 4 is 128. So since that is positive, we know the rate at which oil is being extracted is increasing at t equals 4 hours because E prime of 4 is positive.